This is Coach Neal from Roger Bacon High School, and today we're going to talk about solving one-step inequalities. If you remember back to your lesson on solving equations, our ultimate goal in solving that equation was to get the variable to stand alone. That goal still holds today when we talk about solving inequalities. You want to move everything else to the other side of the equation, away from the variable. You should also remember back from our lesson on solving equations that when we move something, we do it using the inverse operation. So, in order to move anything in an inequality from one side to the other, we must always use the inverse operation. So addition and subtraction, we remember, are inverse operations. So if it's an addition problem, we're going to use the subtraction property, or vice versa. We also know that multiplication and division are inverse operations. So if it's a multiplication problem, we will use division in order to get the variable to stand alone, thus allowing us to figure out what the value of that unknown actually is. So, again, as we think back to our solving equations, one of the properties we used was the addition property. Well, we're going to use that property again. Back then, we were able to solve the equation x minus 8 equals 3. And we did so by adding 8 to both sides. So when we look at the negative 8 and the positive 8, we know that they cancel one another out because their sum is 0. So in this case, we solved and said x is equal to 11. Well, we can now apply that to solving inequalities. Our steps to solve are going to be exactly the same. Since this is a subtraction property, we are going to use the addition property of inequalities, and we're going to add 8 to both sides. Again, we see that the sum of negative 8 and 8 is 0, and we get the variable to stand alone. So simply, when we look at this, instead of saying x is equal to 11, we are now going to say that x must be greater than 11. And we actually will use set builder notation in order to correctly identify that answer. So all values of x for which x are greater than 11. So we know that x could be any number, like 12 or 13 or 14, and so on. This problem would have been solved in exactly the same way, only in this second case, it's less than. So we would say that for all numbers of x, x would be less than 11. But again, it is solved using exactly the same addition property of inequalities. The subtraction property of inequalities will also apply. As you can see, and if you remember back to our subtraction property from equations, when we have an addition problem, we should subtract that number from each side in order to get the variable to stand alone. So back then we solved the equation x plus 8 equals 13 by subtracting 8 from both sides. Again, in this case, we get x to stand alone, and we know that 13 minus 8 is 5. So in this case, we were able to solve x equals 5. Well, now we can also apply that to inequalities. Again, if this is an addition problem, we should subtract 8 from both sides in order to get the variable to stand alone. These give us 0. X is now by itself. So now we are saying, again, using our set builder notation, all numbers of x for which x is greater than 5. So numbers like 6, 7, 8, and so on. When we get to multiplication and division for inequalities, there is just one extra thing that we have to think about. And it has to do with the number that we are multiplying or dividing by in order to get the variable by itself. When that number is positive, nothing really changes. However, If both sides of an inequality that is true are multiplied by a negative number, the direction of the inequality sign is reversed to make the new inequality true. So let me show you an example. Back then we solved an equation like this, x divided by 3 equals 11. And because this is a division problem, we did so by multiplying both sides by the denominator of that fraction, which in this case is 3. So we know that 3 divided by itself is 1, giving us 1x, or x by itself, and 11 times 3 is 33. So we were able to solve and say that x equals 33. Well, because this is a positive number that we multiply by, nothing really changes here. We multiply x over 3 by 3, and again, since this number is positive, we get 1x by itself, and nothing happens to that inequality. So again, using our set Miller notation, we'd say for all values of x, x must be greater than 33. However, in this case, in order to get x to stand alone, we must multiply both sides by negative 3. So in this case, if we say that negative x over 3 equals 11, we multiply by negative 3, we get x equals 33. Well, there's nothing new there. However, when we are dealing with an inequality and we multiply or divide by a negative number, and in this case you can see we're multiplying by a negative number, we must flip the inequality. So we're dealing with a problem that was greater than. Our answer will now be x is less than 33. So as you can see, we did flip the inequality here. The original inequality was greater than. The inequality in our answer was less than. So one more time, using set builder notation, all values for x for which x is less than 33. And that rule of multiplying by a negative number and flipping the inequality also applies to division. Really, nothing changes when we divide by a positive number. The signs will stay the same. So if a is greater than b and we divide both sides by c, it's still going to be greater. Or if it's less than and we divide by a positive number c, the sign will remain less than. However, if both sides of an inequality are divided by a negative number, the direction of the inequality sign is reversed. So here, as you can see, if a is greater than b and c is negative, look what happens to the inequality. Same if a is less than b, we would change it to a greater than inequality. For example, back then we were able to solve the equation 8x equals 48. We divided both sides by 8 and said, okay, well in this case we get 1x equals 6. We can also do that for this inequality where we have 8x is less than 48. Again, we divide both sides by 8, and since we are dividing by a positive number, nothing happens to that inequality. It still remains all values of x for which x is less than 6. However, when we divide by a negative number, again, we see nothing happens here other than the result becomes negative 6. But in this case, when we divide an inequality by a negative number, we must flip the inequality sign. So as you can see here in the original problem, it was less than. In our answer, we are now saying all values of x for which x is greater than negative 6. We also have to deal with word problems, and sometimes in our English language we don't use the exact phrases that we're normally used to. We know that this sign is greater than or is more than, and again we've emphasized the importance of that word is. We also know that this sign means is greater than or equal to. But sometimes within a word problem they may use different wording, like is at least or is no less than. Same holds true for our is less than or is fewer than sign. We know that this is less than or equal to, but there are times when they may ask in the problem, is at most or is no more than. Let me provide you with a few examples. Twice a number is more than the sum of that number and 9. So I've taken that and expressed it as an inequality. And now we would like to solve it. The first thing you should recognize here is that we have variables on both sides of the equation, and we want to get them on the same side. So I would recommend we move the smaller. And in that case, we're going to move that 1n by subtracting it from both sides. N minus n we know is 0, so these will cancel. 2n minus n is n, so we would say that n must be greater than 9. So all numbers for n for which n is greater than 9. So we took this is more than and we replaced it with our is greater than symbol. I'll give you another example. The sum of 3 times a number and 12 is at most, so there's our key word, is at most, and if we look back up here, is at most means less than or equal to, so is at most 5 times that number. Again, we recognize we have variables on both sides of the equation, so I'm going to go ahead and move the smaller by subtracting 3n from both sides. So we're left with 12, because this gives us 0, is less than or equal to 2n. We know that we're going to divide in this case by 2, and because the n is on the right side, we're actually going to read this backwards, so all real numbers for which n is greater than or equal to 6. Now I want you to pause the video and try to answer example 3 on your own. When you're finished, come back and I'll show you the solution. Okay, hopefully you're back. If gasoline costs $3.60 per gallon, how many gallons to the nearest tenth of a gallon can Joe buy if he spends no more than, so if we go back up here and look at no more than, again, it's less than or equal to $20. So in order to solve, we would divide both sides by $3.60, and we would get our solution. G is less than 20 divided by $3.60. For homework, to finish this lesson and to check your understanding, please complete the following examples. Once you complete those, you can check your answers in the back of the book, and hopefully you'll be prepared for tomorrow's lesson.